Hello guys, welcome back. In this video I am going to design an integrator. The aim of this experiment will be to implement an integrator using an op-amp and also to study its frequency response. So before designing an integrator we need to make sure that our calculation is correct. Over here I will be designing for FA as 1 kHz and my FB will be 10 times of FA. So FA is 1 kHz and FB is 10 kHz, and over here I have assumed my feedback capacitor is 10 nanofarads. So as we know, FA is equal to 1 upon 2 pi RF into CF. So my RF will be 1 upon 2 pi of FA into CF, which gives me the value as 15 kilo ohms. And for FB, my FB will be 1 upon 2 pi R1 into CF. Therefore my R1 will be 1 upon 2 pi into FB into CF, which I get my R1 as 1.5 kilo ohms. And as we know, R1 is almost equal to R3, so I have used R3, which is basically ROM. So R1 is equal to ROM, which is 1.5 kilo ohms. So this is the schematic for an integrator which we will be designing. We will see its frequency response and also its transient analysis at 1 kHz with a 2 volts peak to peak amplitude. So this I will show the frequency response as well. This is my frequency response of an integrator. What happens in frequency response of an integrator is that if I have taken my FA as 1 kHz and my FB as 10 kHz, the op-amp will act as an integrator only in that particular period. Before that and after that, it won't be acting as an integrator. So over here I have designed a waveform for an input as sine wave and my output as cosine wave. So this is how it looks like. And over here my input is given as triangular wave, so the integrated output of an integrator is basically a sine wave. So this is my observation table. Over here I have decided upon gain. I have calculated the gain as 20 log dB. My output voltage peak to peak will be calculated upon using the sine wave as my input, and the output voltage whatever we get will be calculated accordingly. And what we conclude from this is, as integrator behaves like an inverting amplifier until it reaches the frequency FA, and then it actually acts as an integrator only during that particular period. So over here we have designed it like that, and the integrator circuit which we will be designing is mostly used in analog computers or A to DC converters and wave shaping circuits. A basic wave shaping circuit is nothing else than a charge amplifier, and they are constructed using an op-amp. So let's start the design of an integrator. I will go to LTSpice, new schematic. My first component will be OP07. So this is my OP07. I'll need 3 resistors. This will be my feedback resistor. This will be my one more resistor over here, and one more resistor over here as well. I'll reduce the size of this. Let me take this resistor the upper side. Now we will need a capacitor over here. Now to power up this input we will need a voltage source. So voltage source. First input to power up op-amp we need 2 more voltage sources. So these are the components which we will be requiring. Now we will connect the wires. This is the first connection, then at the non-inverting terminal, then the feedback, now we need to connect this capacitors to this wire. There's a dot, so that means the wires are connected properly. Now I need to give over here for ground also we need to give some wires, and to power up this VCC and VEE we need wires. So this is the basic connection. Now I will be giving the ground input to all the required connections. These are my ground connections. Now we need to make sure we label them properly. So this will be my V in, this is my V in, this will be my V out. I will change it, V out. Over here I'll give VCC, this is my VCC. It's overlapping, so I will make sure that this capacitor gets a bit aside. Over here again, sorry, we need VCC over here as well. This is my VCC, this will be VEE, negative voltage, and also this will be negative voltage, VEE. So as we saw earlier, our calculations, I will be giving 15K to RF, 10 nanofarads to CF, 1.5K to R1 and 1.5K to R3, which is a ROM. So let me give the values to each and every of them. 1.5K, this is RF, so RF, and RF is given as 15K. This basically directly implies that it is 10 times of FA. This is my FA input, FB, this is my output. 1.5 into 10 is equal to 15K. Now I will give value of C1 as 10 nanofarads, 10 nanofarads, and this will be again 1.5K. Okay, so are the connections done? 10 nanofarads, see, okay. Now over here to power up op-amp, 15 plus minus 15, don't need to write minus because VAA indicates it's a negative voltage. Now over here, as we will be designing a transient as well as an AC analysis, we will give the input as sine wave. Go to advanced, go to sine wave, DC offset will be 0. I will be giving amplitude as 2 volts peak to peak, so I will write over here 1, and frequency is 1 kilohertz. And as we will be designing also an AC analysis, I will need to write AC amplitude as 1. So okay, now it is upon us that what we will be designing first. So I will design a frequency response. So simulate, edit simulation command, go to AC analysis. Over here to linear type of a sweep, my start frequency will be 1, and as I know my stop frequency will be 10K, but for better understanding of a frequency response I will write over here as 20K, and number of points, let's say I will take 100. So this is my AC, which will be linear output. So let's go to simulate and run. So now let me get to output, V out. Okay, so I will go to plot settings, go to manual limits, and make sure you use a logarithmic scale for a better view. So this is the frequency response of an integrator. Over here if you see, this is a 10 dB fall, this is a 3 dB fall as we have in an integrator, and over here my 0 dB comes at 10 kilohertz, and the frequency response is like this, 1K to 10K. This is my FA and this is my FB. So only in this particular period the circuit will act as an integrator. So this is the frequency response, and this is the phase response. This is the degrees, that is the phase shift it will be causing. So this is the frequency response of an integrator. So now if you want to do a transient analysis of the same, we need to go to right click over here, go to simulate, edit simulation command, go to transient, and over here let's say I will give 10 milliseconds as my stop time, and we will be doing transient analysis. So I'll run, this will be my input and this will be my output. So this is the transient analysis of a integrator circuit. So thank you so much guys.